Okay, so this simulation, the first question talks about a magnifying glass we placed over a beaker of magnesium nitrate. So the reason that this part is important is because it's trying to emphasize really what happens. So we did talk about this, that when you have a beaker of solution, technically that means that there is no solid in the beaker. Actually, what's happening is there are ions. So in question number 1, it says magnesium nitrate. So there are magnesium ions and there are nitrate ions. If you have the formula, for magnesium nitrate, and in the beaker we're going to have magnesium and nitrates, okay? So in your little beaker, if you draw one magnesium ion, how many nitrate ions should you draw? Is it 1 to 1? So when you have, sort of like Lewis structures, right? If you have magnesium, which needs to lose 2 electrons, and nitrate only needs to gain 1 to make it negative, how many nitrates do we need? We need 2, or twice the amount, which is what the formula shows us. 1 magnesium for every 2 nitrates. So when you crisscross, when you have an ionic compound, then that helps to rectify like how many do you need. And so things like this, you can't leave this as Mg2O2 because that's not really what happens. We only need 1 magnesium for every 1 oxygen. So ionic compounds, we reduce, they follow the rules, they're a little bit easier to predict. So in your beaker, however many magnesiums you draw, you're going to draw twice the amount of nitrates. And then you can answer the question. How are the number of magnesiums to nitrate related? How are they different? How does this relate to the chemical formula? You can do that now, or you can do it later, okay? So the first page is using the activity series, which is single displacement. So if you want to, right now, with the person sitting next to you or by yourself, you're going to predict whether magnesium, so we're going to start with a magnesium strip. Okay, so a magnesium strip of metal. Is magnesium reactive enough to kick out the metal in the solution? The first one is a little weird, magnesium and magnesium. So in order to get a reaction to occur, there has to be change. So if you have the same thing, is there going to be a change? No. So for magnesium and magnesium, just put no. And then you can do the other ones. Is magnesium reactive enough to kick out zinc? Is magnesium reactive enough to kick out copper? Is magnesium reactive enough to kick out silver? And you need the activity series of metals. This is single displacement. We're going to do the bottom chart as well. So while you're waiting, if you want to do that one too now, is copper reactive enough to kick out magnesium, zinc, copper, and silver? You can just write Y or N, yes or no. So in order for a reaction to occur, we need to see a change. So um, if you were able to do this yourself, then I like this simulation because it actually makes you wait. So the strips are these magnesium strips will be put in the solution, and then they're going to be taken out, and the strip will look different if there is a reaction, or um, it'll stay the same if there is no reaction. So again, when you have no reaction, when the metal by itself, the single compound or single element, is not reactive enough to kick out the element that's part of the compound, then you're going to write no reaction. And you'll see on the metal strip, no reaction. Nothing will be different. When you write the observation, so what you should see, all of them will look bigger, which is fine, but try to make a good qualitative observation. Does it turn orange? Does it turn light gray? Does it turn silver? Okay? And it is qualitative, so you'll see when we do this reaction, maybe Sarah writes silver, but Stella writes light gray. So we're going to, try next unit to use less qualitative and more quantitative observations because those are a little bit less wishy-washy, okay? Everybody should get the same thing. I think with the door open, I can turn the light off. Is that too dark? You guys okay? Just so that you can really see the difference, okay? So they put the strip in. It makes you wait. You have to take the strip out, okay? So did this magnesium strip change? No, you can write NR or no reaction. And then you want to write what happened to the other ones. Magnesium is more reactive than zinc, and copper and silver, so a reaction occurs. So again, don't write bigger because they're all bigger. Even with qualitative, try to be a little bit more descriptive. So the first one, maybe, again, Stella might say black, Sarah might say dark gray. Either of those is good, okay? So then you're going to write the reactions, but you can do that later. And it says to make sure they're balanced and you've included the states, okay? So solid, liquid, or solid or aqueous, there will be no liquid. So now we'll skip 3. You can do that whenever. We're going to do number 4 next. So is copper reactive enough to kick out magnesium, zinc? Remember copper, that's no reaction because no change. And then silver. Which of those metals is copper above on the activity series? So the reason for these colors is because the magnesium is switching. So the magnesium is switching with zinc, and zinc is coming out of the solution. It's becoming a solid. So this is zinc. Zinc is dark gray. Magnesium is displacing copper. Copper is coming out of the solution to become a solid. Copper is orange or rusty, some people will call it. Magnesium is switching with silver. So some of you may have written silver. Silver has that light gray color to it. So the element that is being switched or displaced is now becoming the solid. Okay, so down to chart number 4, copper is, again, that reddish orange rusty color. So we're going to put copper and magnesium, copper in a solution with zinc, in a solution with copper, in a solution with silver. So do your prediction. Which of these, if any, will copper react with? And this time it's less, which makes sense. We use copper to cook with, we use copper in our wiring. We don't want it reacting all the time. It's not good. Okay, so this time copper is much less reactive. No reaction, no reaction, no reaction. And again, why is it light gray? It's because it's displacing silver, and silver is now the solid, which is a silver light gray color. So on the back, that's it's a smaller space and less marks because there's only one reaction to write. You don't need to write the reactions that are no reaction. Okay? So the second part is for double displacement reactions. And so what you're going to do is determine what solid is going to be made. And it's selective, which means each time you do a new solid, one of the ions that you're starting with are going to, like you could even think of them as crossed out. They're not there anymore, okay? So, answer the following questions by circling the correct choice before you begin. If something is soluble, do you see a solid? Yes or no? No. Good. Circle no. So then if something is insoluble, that means a solid, so circle yes. Cations are positive, anions are negative, and when you make an ionic compound, which is what displacement is doing, you're always going to have a plus and a minus, okay? So there are 4 ions you're testing: lead 2, chloride, iron, and copper 2. So what I did was the first 3 deal with the cations, and then the last one, and I tried to bold it, use the anion. There's only one anion, okay? And I tried to save it for last on purpose, so hopefully it doesn't screw up the rest of your work, okay? So in bold there it says, the following ions are in an unknown mixture. A scientist adds the different solutions to precipitate only one solid. So one solid at a time. The other ions, so the ones that are going to be left over, will remain in solution. Determine the solid form using the solubility table. Then write out the name and formula of the solid and the color in the blank. So just to get more practice, so you have to, so it says add Ki, like potassium and iodide, write its name, okay, just again for more practice. And then you're going to figure out the solid. So there is a little bit of space here if you would like to do some rough work. So what we are doing is we are adding Ki to a solution that contains lead, chloride, lead 2, chloride, iron 3, and copper 2. So what you need to do is check which of these is going to make a solid. So when you have the ionic compound you're adding, so all of them are ionic compounds, so the first thing in the formula is the cation, and the second thing will be the anion. So what you're checking is if this ion is a metal, it's already positive. Is this going to go with potassium? No, because it's already positive. So all of the positives you're checking with the negative. There is one anion. That's the one you're going to check with the positive. when you do this, there should only be one solid. If you get two solids, you've made a mistake, okay? So we're using this side, right? So you're going to do iodide plus, and it is kind of set up to help you. You're just really looking for like iodide. You can check it all at once. And be careful, so it is copper 2. This says copper 1. That's not what we have. That is different, okay? So when you add potassium iodide, which one is going to be our solid? There's lead, insoluble, and that's the solid, okay? So what that means is it says ions left. So now lead is gone. Do not write lead anymore. You are not checking lead anymore. So every time you do this, you should have one less ion, okay? And then again, so make the solid, like write the name, write the formula, and then just for, some added, I guess, application, if you make a solid that has lead ions in it, what color will it be? You use this chart here. So again, another way to determine the identity of something is to use color. If you have a solution that makes a solid with lead, it'll be yellow. If you have a solution that makes a solid with chloride, it'll be white. If you have a solution that makes a solid with iron, it'll be red.